Very good morning. In today's video lecture, we can see regarding the maximum likelihood estimation. Okay, maximum likelihood estimation. Maximum likelihood estimation. Okay, so this is the topic that we are going to discuss in today's video lecture. So before coming to this one, why we have to go for the maximum likelihood estimation? That is very important. Okay, so this is nothing but a alternative to minimum variance unbiased estimator. Okay, which is desirable in situation where the MVU estimator does not exist or cannot be found even if it does exist. That is why we are normally utilizing this maximum likelihood estimation. That is the situation where the MVU estimation does not exist. At that time, we are normally going for the maximum likelihood estimation, or the situation where the MVU estimator exists, but it is very difficult to find out. In that condition also, we are going to we will utilize this maximum likelihood estimation. Okay, so what I have to discuss here is this maximum likelihood estimation is somewhat approximately, it is not somewhat, it is approximately equal to that of maximum minimum variance unbiased estimator. So if you find the maximum likelihood estimation as well as if you find the minimum variance unbiased estimator, if you see the final result, we can that the approximation is or both will be somewhat same. With mostly it will be approximately, or the MVU estimator will be approximately equal to that of maximum likelihood estimation. Okay, so that point I will write here. The first point, in situation where MVU estimator does not exist, or cannot be found. Okay, an alternative popular, I call it as popular approach is maximum likelihood estimator or MLE estimator. I call this as MLE. Okay, okay, maximum likelihood estimation. MLE, which is based on ML, that is principle. Okay, so it is approximately, as I told you, approximately you can call it as the MVU estimator. It is approximately the MVU estimator. Clear? So finding the ME, how we can able to find the ME? That's the procedure what I have to discuss here. Finding MLE. Okay. So if you see the books, a lot of things is there indicated in a MLE's estimator, what we had discussed in the mu estimate itself. So we are not going approach all those things. We will take some of the important things what we require. Okay. So MLE for a scalar parameter is defined to be the value of theta that maximize P of x theta for fixed x. Okay. So the quantity P of x theta waived as a function of theta is called likelihood function. Underline that word. Okay, likelihood function is called the likelihood function. Okay, thus MLE is the value of theta that maximize the likelihood function. Underline all this word. Okay, that maximize the likelihood function. I just underline this one. Okay, just underline the words why I indicated here. It's very important. Thus, ML is the value of theta that maximizes the likelihood function. So we can see one graph here. Okay, this is nothing but P of x theta, and this is something regarding theta. So I will write something like that. Okay, this is the peak, theta 2, theta 1. Okay, in the figure theta equal to theta 2. Theta equal to theta 2 is the estimate for theta. Okay, since it is maximized, that is in figure, the above figure, theta equal to theta 2 is the estimate for theta. Since it maximizes P of x equal to x naught of theta, okay, over the available range of theta, over the available range of theta. Okay, this is something regarding the what do you call as maximum likelihood estimation. So finding the maximum likelihood estimate is nothing but MLE for a scalar parameter is to be defined is defined to the value of theta that maximize P of x comma theta x of theta for fixed x. The quantity P of x theta is waived as a function of theta is called the likelihood function. Thus MLE is the value of theta that maximize the likelihood function. Okay. So this is something regarding the maximum likelihood estimator. We can see one example. Okay. That is DC level in white Gaussian noise. Okay, DC level in white Gaussian noise in DC level in white Gaussian noise. Okay, so the observation are x of n equal to a plus w of n, where n equal to 0, 1, etc., n minus 1, okay, comma, a is unknown, w of n is white Gaussian noise with non-parameter sigma square. We have to find MLE for A. We have to find MLE for A. Okay. So we have solution. We have what? P of x of theta, what we are discussing the is in mu. X of theta is nothing but 1 by 2 pi sigma square raised to n by 2 e raised to minus 1 by 2 sigma square sigma n equal to 0 to n minus 1 x of n minus a whole square. Okay, this is sigma. You take the natural logarithm in both sides, so you will have ln of p of x theta equals minus n by 2 ln of 2 pi sigma square minus 1 by 2 sigma square, epsilon exponential will be gone, sigma n equal to 0 to n minus 1 x of n minus a square. Now you take the derivation differentiation with respect to theta. Dou by dou theta of ln of p of x of theta becomes equal to, first term is there is no term with respect to theta, so it will be 0 minus 1 by 2 sigma square sigma n equal to 0 to n minus 1. This will be 2 into x of n minus a. This is with respect to a. It is not with respect to theta. We have to take with respect to a because these are all with respect to A. Slight mistake. Okay, A. So we had to differentiate with respect to A. Okay, into minus 1. So this 2 and this 2 get cancelled. So what will that? Dou by, this is dou by dou A. Dou by dou A of ln of P of x of A will be equal to or which tends to equal to 0, that will gives sigma n equal to 0 to n minus 1, that is 1 by sigma square minus x of n minus A, minus n minus will be plus, so that will be equal to 0. So that brings you sigma n equal to 0 to n minus 1, x of minus A equal to 0, or sigma n equal to 0 to n minus 1. I will take sigma inside that bracket, x of n minus n into A, which is equal to 0, or I can write n A is not equal to sigma n equal to 0 to n minus 1 x of n, or A, which is equal to A cap, can be made equal to 1 by n, sigma n equal to 0 to n minus 1 x of n. This is a case of A. Okay, so if we can see whether it is possible to differentiate further. We have dou square by dou A square P of x of A is nothing but 1 by sigma square sigma n equal to 0 to n minus 1, again by 0 minus 1. Okay, if I take in the second derivative, so that changes to dou square by dou A square P of x of A is nothing but minus 1 by sigma square into n. So here there is no A term, so it is not possible. So therefore I can conclude this A cap, what we have obtained, is nothing but 1 by n into sigma n equal to 0 to n minus 1 x of n is the maximum value, is the maximum value. Okay, so I can write one more sentence here. If an efficient estimator exists, if an efficient estimator exists, the maximum likelihood procedure will produce it. Okay, so this is one example that is related to MLE. Okay, that is maximum likelihood estimate, because in the first case we have taken the first derivative, there we are getting A or A cap. So in the second derivative, if you are getting the A cap, then it is possible, but there is no term with respect to A. Directly we are getting that is nothing but If we made equal to this equal to 0, we will get minus 1 by 2 sigma square n only. So there is no term with respect to a. Okay, so I will stop here. We will continue with the next session, one more example in the next video lecture. Thank you.